So what we're going to do is we're going to talk about acceleration. We're going to talk about, and then when we talk about acceleration, we'll talk about how we can use the same information to come up with the motion equations that we've seen for linear systems and change it over to rotational motion. You've already done this in your book. You've already done reading over this over break, and so this should be nothing new, but this is just so you can see it from maybe my perspective and see some couple of examples I'll do as well. So we're going to look at what variables are used for angular acceleration. Once again, we're going to come up with a relationship between linear and tangential and angular acceleration. So now we've got to think about tangential as well here. And then we're going to talk about the motion equations. How do we take and develop a new set of motion equations like we've used before for linear motion? All right. So we've got a bike now. Instead of going at a constant velocity, we are accelerating. So the bike is starting at 0 miles per hour, going up to 20 miles per hour. Let's assume they do that uniformly. So I would say that's a uniform linear acceleration, which we've used our motion equations for, equations 5 through 10. We know how to track the motion of the bike accurately and predict exactly where everything goes using equations. Everybody agree? So now, what about the ant? The ant's spinning around the tire. Is the ant accelerating? So what direction? So as the bike speeds up, the RPM speed up as well. The rotations speed up as well. So is the ant speed changing? Yes, the ant speed is changing. Remember, the ant has a rotational speed here. All right? So let's pretend we don't know about this other thing called centripetal acceleration. That's a separate topic. In fact, that topic comes after this one in my slide presentations. So what about other forms of acceleration for the ant? Tangentially, right? I mean, if we had tangential velocity before. Remember the string spooling off of my wheel? So if we have a tangential velocity, guess what? We have a tangential acceleration in the same sense, all right? So the ant has a tangential acceleration. What about acceleration? What about rotational? Well, yeah, it says right here, right? If our RPM is increasing, that means he's rotating faster and faster and faster. So rotationally, he's accelerating too, or she, should I say, because all ants are she's. Well, all the ants will do the work at least. That's true. It's like bees. That's the true statement, right? Honeybees, they're all females. Ants are the same thing. No, there's a very small number of males. Same thing with ants. They're drones. Same thing with ants. That's right. So yeah, the ant's accelerating in the angular direction as well. It's rotating faster and faster and faster. All right. So if the bike speeds up or slow down, the wheel's RPM does what? Which we call, by the way, the angular velocity does what? It speeds up or slows down as well. It increases or decreases. All right. If the bike speeds up, the angular velocity increases. If the bike slows down, the angular velocity decreases. All right, and you notice here I've drawn over on the bike, we've got our angular velocity, omega. If we've got a change in our angular velocity, what's the definition of a change in angular velocity versus time? Or change in any velocity versus time? It's an acceleration, all right? But now it's an angular acceleration. New variable, it's alpha. It looks like the fish, all right? That's a lowercase. What's the capital alpha look like in the Greek alphabet? This is lowercase. That's lowercase. It just looks like a capital A. Maybe with some fancy stuff on top. Boy, this is really out of... Okay? So that's a capital Greek letter alpha and a small. We're using the smaller for acceleration, the fish-shaped one. All right, and once again, I'm going to show you, we've got this wheel. I'm pointing to the center of the wheel is rotating as well. So our omega and our alpha are on our wheel rotating. What direction do we use? All right. So choosing our signs and axes. For x and y, we use plus x plus y. We draw our plus x, y axes, right? For rotation, we actually would show which way it's rotating counterclockwise or clockwise. And we define which one of those is positive. In this sense, I decided to call the rotation in the center of the wheel here, clockwise is positive. All right, and I'd use that as for my sign convention is what we call that. So we've decided Clockwise is positive for our sign convention here. So now we can go back and look at some of the stuff we did before. How do we calculate the bike's average linear acceleration? And we're going to assume that this is evenly speeding up, so it would also match our instantaneous acceleration. How do you calculate linear acceleration on an average basis? It's delta V over delta T. Sorry, my X needs to be subscript. Circle that. That should be a subscript. And you notice I'm giving you an X direction up top here as well. So yeah, just do delta V over delta T, right? And it's easy math here. It's 10 seconds, so it's 0.894 meters per second squared. How do you figure out the bike's tangential acceleration? But is that for AX or is that for AT for alpha times the radius?
Isn't AT equal to AC?
It's not.
Oh, isn't it equal to negative AC?
It's not.
It's equal to the linear acceleration.
Yeah, it's equal to linear acceleration. Your linear acceleration is exactly equal to tangential acceleration. All right? And the reason is it's the string coming off the wheel, right? Whether I'm rolling the bike along the ground and measuring the speed or the velocity of the bike or the acceleration of the bike, if I were to lift that bike up and keep the wheel spinning at the same speed and spin off the spool of thread, that thread's going to be moving off regardless of what direction I pick, in a tangential direction at the same acceleration the bike would be if it were rolling. Does everybody agree with that statement? All right. How about the angular acceleration? How am I going to calculate the bike's angular acceleration without going through a fancy derivation? What do you think I'm going to do? So, two ways I could do it. One is I could use delta V over delta T like I did up top here. Now I'm going to use delta omega over delta T. So the process I used here, I'm going to use down here. All right. The other process is I could use the relationship between alpha and A is alpha times R equals AX. All right. That's from number 9. I got the 29.3 from problem number 9. All right. And how are AX and A related? I could also have used on this last problem, I could have taken my AX value and just multiplied R times alpha equals AX and figured out what alpha was on the last problem. All right. So there's our completed table just showing the relationships. And these are the key relationships we're talking about. That guy, and that guy. Okay? So let's do a couple little calculations here. And at some point here, you're going to have a couple new slides that you don't have yet. And I'll make a note. If there's any slides that you don't have and you want me to print them off, just write down the slide numbers and I'll print them off after the fact for you. Okay? The blank ones. And then you can fill them on because I'm going to post this video online for the folks who aren't here. So we got to find the linear position of the velocity of the bike at time equals 5 seconds. Suggestions? You're going to do what? Uniform acceleration and use equations 5 through 10, all right? So I'll make some assumptions, give my initial conditions, write down my formula, is equation 5, plug in my initial conditions, and that's my formula that specifies for this particular problem, I'm x of t equals 0.447 t squared, and then I can just do what? Plug in 5 seconds for t. And I got 11.2 meters that we've moved in 5 seconds. Same thing for the velocity, blah, 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 and you get 4.47 meters per second. Okay? What about for 10 seconds? What do? I get to reuse my equations, right? So I don't really need to formulate new equations. I'm just going to reuse the equations and plug in 10 instead. And you'll notice what happened with my position. When I doubled my time, what happened to my position? It quadrupled it. Why?
squared.
Yeah, because we're t squared, all right? So x is related to t squared, not t. So if I double the time, I'm going to square the value. If I triple the time, I'd have 9 times the distance. For velocity, on the other hand, if I double the time, I double the velocity. And as you recall, this is a good review of chapter 1-2 concepts, where we talked about the initial ideas behind position, velocity, and acceleration. And we have uniform acceleration. We found our acceleration versus time graph is horizontal, constant function. Our velocity versus time graph is a linear function. So if I double the input time, I double the output. So that's what this doubling effect you're seeing right here is because we have a linear function. This is quadrupling because we have a quadratic or a squared function. So that goes right back to all those graphs we were making of position, velocity, and acceleration. Okay, next. Let's find the angular position of velocity of the ant at time equals 5 seconds. What do you think I would do? What method? Same method?
No.
I don't know those yet. I don't know what you're talking about. Those don't exist. Not until 3 slides later will those exist.
Could you find the do you know the circumference of the
24-inch tire.
so you find the circumference of it and then you can divide the distance traveled by the circumference and that'll give you S, and could you do theta equals S over R?
Yeah.
And
Yeah, so we can do a conversion using divide into the circumference into this and then convert it to proper units. Or I could use what? A little bit faster method. How about x equals r theta, which is your arc length formula. So we can use x equals r theta. What units am I going to get when I use x equals r theta? X is in meters, r is in meters, and theta is in what units here? Radians. It's in radians, all right? So this will give me, if I solve for theta, this will give me theta in radians. All right, you got to keep in mind units on these because theta has all sorts of units: radians, degrees, rotations, you name it. Those are the 3 common ones. There's other ones though. Gradients. There's a couple others that are used occasionally. So we could just take our answers from last time and just divide by r. All right, and we'll get what type of answer out of this? And you'll notice I did a conversion over on the right here. 1 foot, I converted into meters. Got to be careful with your units here. And I got 36.7 radians. Okay? And if you wanted to, that's 5.85 rotations. You can do any conversions you want. How did I get 5 and 10/12 rotations out of that? Roughly. How did I get that? And why did I do that? Nope. I want to plot it like a clock on here to figure out where it is. That's why. I'm doing a 12-hour clock just so I can figure out where to put it easily. All right, just an easy way to put things in clock. So there's another way of measuring angle. Your clock. What hour you're on the clock, right? How did I get this roughly 10/12? What did I do, Ashwin? Take 0.85 and multiply it by 12. If you think about it. I'm basically taking my conversion factor that I did not show here is 1 rotation is 12 hours. So I did multiply by 12 hours per rotation, and I converted this into hours. But I really didn't care about the 5 portion of it. I only cared about the 0.85. So I just took the fractional piece and multiplied by 12. So it turns out to be about 10/12 of a revolution. So I'm going to move 10 hours. I'm going to move 5 complete rotations and then 10 hours on a clock around. All right. So omega, you can come up with omega doing the same type of thing. Use the same type of relationship. Divide the velocity that we got in the x direction, divide it by the radius, and out pops your answers again. All right, and you can crank out all your numbers again. Okay, and for 10 seconds, I can do the same thing. All right. So one thing is it's easy to convert directly from linear values into rotational values. All I need to know is the radius. All right. If that's something that you need to do. That's pretty easy to do. But is there another way to do it without finding x and vx first? Could I do this directly? What equations? I don't know about any equations. I still don't know any equations. We had to derive those equations. So I don't want to use these equations and then go with all the math. What am I going to do? Let's do a little substitution here, see what happens. All right. So for any time I see an x, I can replace it with r theta. Anytime I see the variable vx, I'll replace it with r omega, and so on and so forth. And when I do that, here's what I get. Oh, by the way, this is equation 5 and 6. I can do it for all the equations up here, right? I'm just focusing on 5 and 6 right now. Yeah, you'll notice I have a common term going through everything here, so I can factor it out, cancel it if you want to think about that, or just cancel it out in every term. You can only cancel if thing shows up in every single term, right? Nice color coding here to make it easy to see. So I can cancel out all the r's, and what do I get? Look at that. Looky, looky. We got a nice new set of formulas that's angular position versus time, angular velocity versus time. I can do that same method on every single equation on our special sheet that we came up for motion equations in 1D and turn it into 1D. Rotation is just like 1D, right? It's just a 1D rotational dimension instead of a 1D linear dimension. And so all I have to do is take all my x values on this page of equations we have, divide by r, and it gives me omegas everywhere. Thetas or omegas or alphas. All right? So that looks familiar. That's what Gabby's been bugging me about. Give me the equations. Put the equations up.
From r theta t to r whatever that your w thing is.
Here?
Yeah, how'd you go from the one above it? There's two separate ones. Oh, okay, that's fine.
I took Vx and replaced Vx with R omega. Okay. Yeah, the T here, that's your, like x of t, your function notation in math.
Yeah, I thought you were going from like the top function to the bottom function there.
Yeah, are you good?
Yeah.
All right. So basically, we can use our brand new equations that we worked out here and do this a little bit more directly here. All right. So now, instead of using x naught, vx naught, and ax, we're going to use theta naught, omega naught, and alpha. So we already calculated alpha, right? Now, and this is where you remember, rotational units can be, for the rotation part of it, can be rotations, radians, degrees, clock hours, whatever. And your time units can be whatever time units you want, all right? Standard MKS units, I would argue you would use radians per second. But it depends on the problem as well. For example, the question was, how many rotations does the amp make? I would use rotations for my angles rather than radians. So you want to think about what are the best form of radian, best form of degree measures that you need, and time measure for you to solve the particular problem. All right. For example, what type of units would you use for you on Earth going around the Earth? You'd use probably rotations per. You have one, what's your omega going to be? One rotation per day. All right. So I'd use rotations, and I'd use days for my rotation unit and my time unit. So we make one rotation per day on Earth, by definition, right? About the Earth's axis. So you'll use whatever units fit the problem in reality. But in a lot of cases, you got to be careful because sometimes we need to use the radians per second units to make our problems work out properly. All the basic equations we started with, x equals r theta. Vx equals r omega and ax equals r alpha. Those rotational units have to be in radians per second squared. For those three equations, those are definitely you got to use radians in those cases. All right. So, like I said, notice my choice of units here. I'm going with rotations here per second squared rather than radians per second squared because I want to know how many times the amp's rotating. And once again, I just plug in. I know what alpha is. It's half of the 0.467. The omega naught is 0, and theta naught is 0. That's going to be 0.234 t squared. And so if we look at the dimensional analysis, times in seconds, right, when we're squaring that, and what's this unit here, the 0.234? It's rotations per second squared. So the time units will cancel just fine. We'll be left with rotations in this calculation. So when we plug in 5 seconds, we get 5.85 rotations. And that matched our other calculation we did. But we're doing it directly. We don't have to go through any. We'd have to go through x first, calculate x, and then do a conversion. So if we happen to know our initial conditions in radians, radians per second, radians per second squared, we can use your own special motion equations for our rotation. Omega, same thing. Use this formula. We've got acceleration times time plus omega naught. Omega naught is 0, so we're just left with the 0.467 t. Toss in our time. There's our answer. It matched up with our other answer. For 10 seconds, same thing. Just plug them into our new equations. Easy enough. Everybody agree?
I thought you said we needed to do radians, was it not that?
If I'm using x equals r theta, Vx equals r omega, Ax equals r alpha, I've got to use radians per second for that, because that's defined based on radians, unitless quantities. Radians are unitless quantities. They're based on, what's a radian? What's the definition of a radian? Who knows? When do we get unitless quantities? Think back. When do we get ratios? So what's a radian? It's a ratio of something. It's a ratio of. Stop looking things up.
No, I wrote it out. Arc length is S is equal
He's
to
as he's looking at his phone there. All right, okay. He's watching my printout over there. It's a ratio of your circumference to your diameter of a circle. That's what one radian is. All right. And by unitless, why is that important? Why is it important to use unitless, if possible, quantities? Let's call them universal quantities. That way the Martians can also use the same math, and we can communicate with Martians using mathematics. Right? And they don't need to know what our basis for things are. Like 360 degrees in a circle came from our rotation around the sun. All right? Martians don't use 360 degrees for a circle. They use what? They use like 720 degrees in a circle.
Wait, I have a question. Actually, never mind.
All right? But they would use the same number of radians we do. So radians would mean the exact same thing to Martians. All right? So here's our good old formulas. And all we need to do is apply our relationships between linear and rotational variables, which we did right here. And we come up with a brand new set of equations. And you have this sheet. I gave you this sheet. And you have it in your notes, too. You took notes on this. All right? So there's nothing new here, folks, is what my conclusion is. All right? We're just doing things turning instead of going in a line. All right? So when can you use constant acceleration equations, 5 through 10? Only when you have uniform acceleration or constant acceleration. Uniform means constant, all right? So what would cases like that be when you have rotation instead of translation? A bike if we're accelerating uniformly. Uniform circular motion, the acceleration is 0. Because you have constant speed for uniform circular motion. Okay? So technically that's constant acceleration of 0, which is sort of the moot case. Another example, real life example, when something's speeding up at a constant rate to come up to speed. Or slowing down. How about your car? If you were to put your pedal to the metal, maybe you could average it out. Remember, we have uniform acceleration, but then we can also do average acceleration just to get a rough idea of how things are working. So we could say if you're speeding up in your car to like merge into traffic, for example, maybe you say, okay, roughly speaking, we'll just take an average acceleration, call that, roughly speaking, uniform. You could also look at your tires on your car and calculate all the stuff in the tires of your car. Why would you want to calculate these types of things on for the tires on your car? From an engineering standpoint, if you're designing tires for cars. You want to see, you're right, you want to see these accelerations turn into forces, and these forces you can look at how durable and how you have to design them so they don't fly apart as you're driving along the road. That would be a bad thing, all right? So you need to know these things. Your washing machine spinning up to full speed. The Turkish twist spinning up to its full speed. And then it goes constant for a while, then it slows down. So anytime you have something spinning up or slowing down, it may or may not be constant. You may also want to just assume it's constant just to get an idea, roughly speaking, what's going on. All right? 5-step process is the same. We're just using rotation instead of linear. All right, so here's an example. Did you guys probably have this one in one of your web assigns? I'm guessing. Web assign 7, A, B, or C. So you have a coin you drop on the ground. So what do you do to solve this problem? Well, if you were doing it in 1D to watch something move across, we draw an x-axis, right? But we're going to draw a angular axis, which I just drew in the center of that circle. I'm defining pluses clockwise in this case, and in the x direction, I call that plus x. So I'm going to look at both of these side by side, it looks like here. And I've got my ant stuck to the coin, or the worm I just ran over in red, I guess. So here are my initial conditions for the coin. I just need some sort of reference point of the coin to know where 0 is, all right, so I can track the coin. So it's nice just to have an extra worm around that you can squish over and run over the ant so it sticks to your wheel so you have as a reference. What's negative? The fish. Why is alpha negative? Good question. The coin's slowing down. In the last line. How does it? All right. So coin. So there's some frictional forces that are slowing it down. Right. Essentially. Okay. Here it is later on. I don't know exactly how far the coin is away or how many times it's rotated, but I just showed the rotation. It ends up at some other point. I guess where we started at the 6 o'clock position is 0 radians, and we end up, I just guessed it like a 2 o'clock position later on. I don't know what it is. We're going to calculate that, right? So in the linear motion, you end up moving 0.748 meters. You can see the answer that is the answer for this problem. But we're going to figure out rotationally what happens here. So we know at the end, we know our final omega is 0 radians per second. And we need to figure out the final position, maybe like the 2 o'clock position I have drawn here. That's just random. I picked that. I don't know if that's right or not. And more importantly, we need to figure out how far this is rolled. Okay? So what are you going to do? Constant acceleration, make our assumption. We're going to assume that we're slowing down uniformly. We're assuming some sort of frictional force that's constant throughout to slow us down. Once again, equations 5 and 6, right? Well, I don't know. What's the best equation to use for this one? Well, 5 and 6, I'm just checking off what we know. So same old problems we've done before. We're 1D. We're doing 1D rotation instead of 1D linear. So there's 2 equations, 2 unknowns if we do it this way, right? We have time and theta and time. So we can actually use equation 6 to get the time, right? Solve for the time in equation 6, plug it into equation 5, and we'll get our theta 1. All right? Or do what? What equation? We've got our initial velocity, and we got our final velocity. Equation 8, right? Oh, by the way, in the old days, I used to call that equation 9. I promoted it to equation 8, though, because it was more important. Should you use, on the AP exam, should you tell them, oh, I'm going to use equation 9 now? No, these are my local numbering systems, so do not do that. All right, we know everything here except the initial position, and you plug in your numbers. And sorry, I flipped my numerator around here, so you got to flip that around. My answer is correct in here. So you get, that's going to be a positive over here. And that's how I knew I flipped my denominator around, because I got a negative by mistake instead of a positive. So crank it out just like we've done before. All right. Once another time we like to use the equation 8 to solve things. Tossing something up in the air, right? If we know the initial velocity, tossing it up at the top, at the apogee, it's 0, and we can use the same relationship. Keep in mind those shortcuts. Yep.
Seeing that you know delta W and you know your angular acceleration, could you use angular acceleration equals delta W over delta T to find time?
Yeah, you could use that too, because your average and instantaneous are the same. So you could come up with your delta T for that. What do they ask for? They don't really care about time though in this problem, so they only care about distance. So if you're doing the AP exam, you're looking for time. You're looking to save time on the exam and not to find time. So don't find time if they don't ask for it. I guess is a rule of thumb here. So if they're not looking for time, they're looking for distance. See if you can use equation 8. All right, and you'll save yourself some time solving problems. Remember this problem? And remember what the question I asked with this? I can pull down on a rope with 20 newtons of force, or I can hang a 2 kilogram mass on this that applies 20 newtons of gravitational force. And do they both accelerate at the same rate? The answer was no. The first case, if you're just pulling down with a string, you accelerate at 4 meters per second squared. But as you recall, we went through this process to solve. Good review of this for your term exam here. If you have two objects, you got to do two free body diagrams. If you have rope attached to them, the key here, as you see in the yellow box, is that if the 5 kilogram object moves a foot to the right, well, the 2 kilogram object moves a foot downward. They're on the same axis. So just use the rope as your axis and twist the axis with the rope. And that's what I did there. Oh, this is supposed to be blue. Could have sworn I made that blue. There, blue. All right, so we just rotate our x-axis for the object that's moving downward. And you work it out, and you end up with 2.86 meters per second squared when you go through this process. So remember that fun process? All right, now, so let's go ahead and use this to answer this problem. Now we've got an ant decided to climb up on top of the pulley right when that block was released. And I want to find out if the block drops a half meter to the ground, where's the ant just as the block reaches the ground? And I want to know, you can find the time, angular velocity, angular acceleration, stuff like that. All right? So how would you do it? Using our angular motion. So now we're looking at an ant moving in a circle on that pulley. By the way, what assumptions do we need to make to solve this problem? A massless frictionless pulley. Otherwise, if it had mass, we'd have to add that mass into our equation as well. That would slow down our acceleration. If our rope is not inelastic, then we get some real problems because now those two objects aren't moving together, and at least not at the same rate anymore, because one's going to be stretching, the other one might be going the opposite direction for all you know. The frictionless, if we had friction, it would slow us down as well and reduce our acceleration. So we've got to be careful to keep those in mind as we do these problems. So, well, we're going to start with, we already have acceleration of the system, so we're going to use that. What are you going to do with that acceleration? What do you think? And we got to look at the ant, which is turning in a circle. So recommendations? To do what first?
Couldn't we just use delta x equals r delta theta?
Do you have delta x?
It says it dropped a half a meter to the ground.
Yeah, we're eventually going to do that, because that's one of the things we got to find. So yeah, we know how far it's dropped, so we can actually convert that linear distance into a rotational, how many times the thing's rotated directly, just like Ben said. We can use x equals r theta to directly come to that one particular answer. I'm going to do things maybe in a slightly different order, but yeah, that's what I'm going to do eventually. I'm going to just set this up, just show you all the different problems that you can solve with this. So we got some initial conditions. We're putting the ant at the top. I'm going to call that 0. That's going to be my 0. I've defined plus rotation as clockwise, starting at 0 radians per second, and I've converted our linear acceleration to a radial acceleration. I don't need any of that, though, to figure out where the ant lands at the end or stops at the end, as Ben said, because I can just take the distance half a meter and see how many rotations half a meter equals on my little pulley there. So I can divide by what to get that? I can divide by the circumference if I want to figure out the rotations, or divide by 2 pi to figure out the number of radians. And I'll do that in a second here. So we know that x equals 1.5 meter. So here's what Ben just told me to do, right? So I'm actually dividing by r. And remember, this goes back to my comment from before. X equals r theta. Theta is in radians. And so that answer gives me radians. If we wanted rotations, we could have done what? Instead of dividing by the radius, we could have divided by the circumference, right? Instead, 2 pi r instead of r. All right. And that's how I did my conversion at the end. I didn't have enough room to show my conversion, but that's, you know how to do these conversions. So as you saw, I just spun this. So you can see, so here's what it does basically. Once, 1.6 times. All right. So there's our position, final position. How about our final velocity? Equation, my equal sign's a little bit off here. Better note, fix that. What do I do here? To get my final velocity, equation 8 can get me that directly. If I had time, I could plug it into my equation 6, but I'm going to use equation 8. Solve for your final velocity. Omega not 0, so I'm just taking the square root of both sides, plugging your numbers, you get 13.5 radians per second. Remember, omega in these equations these are all in radian units for this sheet of equations. Then I can plug that in to figure out time. And of course, you know that there's more than one way to go through these equations. So I'm just showing you one way to get to these answers. Our tangential velocity, as Jade had mentioned before, is the same thing as our linear velocity, right, Jade? I think you told me that, right? And that's our thread unwinding from a big spool analogy that I'm using to figure that out. Centripetal acceleration, which is technically my next topic in this presentation, but we've already done it. Turns out it's 9.11 meters per second squared. All right, as compared to the 2.86 meters per second squared. Your centripetal accelerations can get really big really quickly. How big is 9.11? Is that a big acceleration? Compared to like a Tesla. That's like how quick a Tesla is. That's a huge acceleration. That's 1G almost, right? So that ant is feeling a 1G force acting on it in a radial direction. So it's getting pretty mangled in the radial direction. Remember, the centripetal force is in the radial direction. Whereas the tangential, it's also feeling a force applied to it tangentially. So if I've got a force, and let me just draw this in the ant. I've got a force. If the ant's moving this way, as it's VT, AC is this way. All right. We've also got a tangential acceleration here. So we have what? We have some sort of force then that matches this, right? If we have an acceleration, if we multiply mass, we have a force. What force is this? That's our centripetal force, right? And we've got a tangential force as well. What are these? What are causing these? What's keeping us in a circle? What force is keeping you in the circle? There's got to be a centripetal force acting inward to match our centripetal acceleration. So what force is keeping the ant in the circle? What is it, Ashwin? What? Gravity acts downward. And you can see this one's not downward right now. This one's rotating in every single direction. There's a force that's keeping this ant in the circle. And let's say if we have here's a pulley right here. I've got an ant like on the edge of this pulley right here. And I'm spinning it around. And the ant just is just staying there.
Is it the total force of the centripetal force?
No. There's a force that keeps the ant in the circle. What is it? I don't know. I think it's called force sticky ant feet.
Wow.
You know how bugs have really good adhesion to surfaces? I don't know if I'd call it friction though, because it's something a little bit more interesting than friction, I'd say, because they actually cling to surfaces. It's force cling somehow, right? So they have little hairy paws on their, what do they call their ends of the feet? Paws? I don't know. All the tiny little fibrous things at the end that can clutch onto all sorts of things really quite nicely. Glass. How do you climb up glass, right? Do ants climb up glass? Yeah, all the time. So they have force sticky feet, I guess it's called. I don't know if I'd call it quite friction because I think it's something a little more interesting than friction. All right. So it's force clingy feet or something like that. All right. It's force whatever, Spidey force, right? Spider-Man, right? They can't see that in my video. So Spidey force. So that the clinging little feet that ants have allow them to, are just the force of keeping them on. All right. And there's a force that's acting tangentially as well. The question is, what's your total acceleration? How do you get your total acceleration here? How do you get your total acceleration? These are perpendicular to each other, right? These two accelerations. So there's a right angle between these two. So to get the total, you can use Pythagorean theorem. All right, that's what I did right here. So that's your total acceleration. All right. Modeling activity. So you have your packet you started working on over break. So now that you guys are so smart, you know everything about everything. Well, to a point at least. Now we can actually take a look at a real system here and do some modeling. Modeling means come up with a map. Too loud. So here we are at Canopy Lake Park. And this is actually that's Stephen Jasek. That's me. The blue and white striped horizontal shirt is Mike Sheets. So this is a famous picture. I think that's Julie Mitchell. But that's our class on there. And there's one weird guy in here too. This guy right here in the black shirt. That's Peter Tardif. This guy right here. Some weird guy got on the ride with us, and he was doing weird things. But what happens on this ride? The ride, I broke it down into 3 phases. First, what happens? Now you can see people. That's Pat Moore. See there. There's Julie Mitchell. That's Kim Islip. That's Peter Tardif, and this is the weird guy with the skull. So what happens? At first, what does the ride do? It accelerates. It speeds up. For how long? I don't know. You can measure it. That's why we took this video. From this video, I actually measured this. So these numbers I gave you on the handouts are from the video. I actually threw it in LoggerPro and analyzed it. What can I use to analyze it in LoggerPro? I think I actually used, I might have used Julie or like Peter's white hat. And every time it came around, I just click, 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 and hit the hat every time it came around to a certain point on the thing, like at the top of the thing. All right. So I use LoggerPro just to run through it. This was a lot of points in LoggerPro. No, I didn't like the weird guy with the skull. But I needed something easy to pick out, so I was probably using Peter's white hat or something. So the first phase, you just speed up. And once again, we got to make some assumptions to simplify our process here. We're assuming what? Constant angular acceleration on this, right? Now, tell me if you notice anything else interesting that you see as you watch the video here. What else could I use for measurement? Well, I don't want to learn more, actually. I just wanted to play. It's not lunchtime yet. It's 20 minutes to lunch. Plus, you guys played for the first 15 minutes, so you're going to skip lunch today. I was not playing. In any case, oh, thank you very much for this very uninformative. So in any case, phase 2, you go to constant speed for a while. And by the way, at that constant speed, what do they do on the Turkish twist? They drop the floor on you. And so hopefully they're dropping the floor at a high enough speed such that you don't slide down the walls. What are the walls like?
They're like sticky. No,
They're not sticky. They're metal.
no, they're not.
Smooth metal, they are.
I don't believe it.
It's metal.
They feel like rubber.
But they have holes punched in them. To give it a little bit more surface. Because you got to get to a certain speed so that your what? US reaches the point where US takes over from UK, right? And that's what your handout goes through. And then after your ride's done, they slow you down to a stop. So the whole idea behind this Turkish twist packet is for you guys to come up with, now that you know how to do rotational motion just like linear motion, come up with equations that map out what the future position velocity are for a constant acceleration for phase 1, phase 2, and phase 3. And those 3 have to be linked together, right? How do you link the 3 together? How do you link those three sets of equations for phase 1, phase 2, phase 3 together? What links them together? We've done stuff in multiple phases before. Rocket shoots up, then engine runs out. What links the two phases together? The final velocity of phase 1 and the final position of phase 1 roll into the initial for the phase 2. Bonus point for Dylan. That was good. And that's really on the Turkish twist modeling activity. That's all you got to do is you're going through that process instead of linear motion. Now you just got rotational motion. So if you think about it that way, this packet's a pretty easy packet to do. All right, and it's a quiz grade. You get a 95 if you get all the questions right. What do you mean, excuse you?
What packet? Yeah, what packet?
Your Turkish twist. You've already done 1 through 4.
Going.
Oh, you want more than that? You want more than 95? You do the Excel spreadsheet, which maps it all out and graphs it for you in Excel. Then you get 105.
Oh.
How's that?
Wait, am I supposed to use that video?
I actually gave you the data out of the video, so you don't really need it.